In today's fourth lecture, we are going to talk about only the explicit Runge-Kutta method, because that has been found to be one of the most accurate method. As we go along in this course, we will find out why it is preferred, and we will also talk about another classification of differential equations, time dependent differential equations. This is related to the non-autonomous versus autonomous system, and when we express it as an evolution equation, if the right hand side does not explicitly involve time, we have what is called as the non-autonomous systems, and in this course we will be mostly focusing our attention to non-autonomous systems, because many of the applications will see the time does not appear explicitly. And coming back to various Runge-Kutta methods that we talk about, we begin by two-stage Runge-Kutta method, which we have shown here as the RK2 method. This will be followed by RK3 and RK4 methods. However, we will be not discussing in greater detail about RK3 method, because that will be given to you as an assignment that will be doing as a first assignment for this course. Having exhausted this discussion on Euler and Runge-Kutta method, we introduce the multi-step method by talking about 3 time level methods, and in this we will be talking about Adam-Bashforth scheme and also the leapfrog schemes. We will find out the pluses and minuses and why we do not want to use it. Finally, talking about this ordinary differential equation solution methods, we need to talk about what is called as the stiff differential equations. If in the solution of this ordinary differential equation multiple length or time scales are involved, then what we encounter is a specific difficulty, which is characterized by this term called stiff differential equation, characterized by the parameter stiffness ratio. And then we talk about the classical methods of solution of stiff differential equation by trapezoidal method. This will be the final topic of today's talk. Here that problem, we noted that you can adopt single step method from the physics point of view, that you do not get into a numerical or spurious modes, but you could have multi-stage. And what is that? And the first milestone in that road would be a two-stage method. We have talked about some of those. We have talked about Euler-Cauchy method. We have seen that if you are marching the solution from T n to T n plus 1, you have to evaluate 2 additional quantities, which we called as K 1 and K 2. Okay. So, in that same class, Runge-Kutta methods also fall. They are single stage, multi-stage methods. We noted that if we are trying to solve an equation of this kind, and we are going from one time step to the next one, then the Euler method, forward Euler method required that you take a slope here and you extrapolate, and that is where you get, and that could amount to some error. Or you could draw the tangent here, which is parallel to this, and you could get this. That was your backward Euler method. That is what we talked. So, here in the multi-stage method, you say that you do not generate all your information from either of these terminus points. Instead, you also look for some intermediate point from where you keep on getting information and use them and improve the accuracy of the method. So, that is the whole idea, that you do get information from multiple stages in between these 2 time levels T n and T n plus 1, and eventually you get the solution as a weighted average of all this information that you have culled from this terminal points plus those intermediate stages. So, that gives you enormous leverage and freedom to choose methods from. For example, if you restrict your attention to just simply explicit methods, then you would keep on calculating, let us say, slopes at m such points. So, m could be at your disposal, you decide upon how many stages you would like to. So, we are suggesting that we choose m such methods, and we have chosen this stages, intermediate stages, in such a way that each k i's could be obtained from the information you have collected up to that point. So, for example, we have information at T n. So, we could immediately calculate k 1. Okay. Having obtained k 1, what we could do is we could obtain the solution at a next stage, which is in between T n and T n plus h. So, that the C 2 is less than 1, right. So, you have some intermediate point, which is C 2 h from T n, and then there we also calculate the dependent variable as some kind of a weighting of what we have just now calculated in the previous level k 1. So, that means in evaluating k 2 you need k 1, in evaluating k 3 you would require k 1 and k 2, and so on and so forth. So, this is essentially a recipe for explicit methods. Okay. So, that is what we said, that we will keep our will be keeping our attention focused to explicit methods. We will obtain the slopes at m such stages. Each k i's will be obtained from the cumulative predecessors. That is a distinct feature of all explicit methods, and eventually you get the final accepted solution as the previous time step solution plus this weighting factor times this k 1. So, this k i's are nothing but something like your delta u, right. So, they are the delta u's, and this W 1, W 2 and W m, they are the weights that you associate with the method. So, essentially now if you look back, you have to decide upon what are these coefficients C 2, C 3 all the way up to C m, and here you have A 21, A 31, A 32 and so on and so forth. And finally, these weights are also our unknowns. So, these are basically the parameters of the Runge-Kutta methods, and they have to be obtained. One of the easiest ways, of course, work out the Taylor series expansion of the function u n plus 1 in terms of u n, and the number of terms that you match from your theoretical Taylor series expansion. So, what we mean by theoretical Taylor series expansion is we are writing u of t n plus 1, this we are going to write u of t n. So, since your governing equation is well we are looking at ODEs. So, if this is what we adopt our governing equation as, then we can keep on adding whatever information that we have, delta t, which we will be calling as h, let us say. So, h times u prime and h square u double prime, and these are all evaluated at T n. So, and so on and so forth. So, this is your analytical expression, whereas the numerical solutions we have denoted so far with the simple superscript like this, and we have said that our method would be something like h phi of t n plus 1 t n u n plus 1. Okay. And of course, it will also be probably a function of h also. So, what you essentially do is you obtain two Taylor series, one from the analytical expression, one from the numerical method. You keep matching them, and the number of terms that you match from either side would define your order of the method. So, if I go up to say h squared, that is a second order method. If I decide to go up to h cube, that will be our third order method, and so on and so forth. So, this is the essential idea in a nutshell. So, you can just work out one such simplest possible method would be an explicit second order Runge-Kutta method. So, here we are of course fixing m equal to 2 and we will first evaluate k 1, that would be the delta u at the starting date, h times f evaluated at t n u n, and then next we will be adding to this part the independent variable incremented by C 2 h and the corresponding dependent variable incremented by A 2 1 k 1, and so that the accepted solution at the n plus 1th level would be the predecessor plus the weighting of these two increments k 1 and k 2. So, very easily you can see that we have 1, 2, 3, 4, 4 unknowns. So, for this second order methods we will have to work out some ways and means of evaluating these 4 unknowns. Okay. So, what we do is as I told you that we will write down the theoretical estimate in terms of the Taylor series, and as you can see u prime as given here is f. So, that is your h times f. U double prime, now we have to realize that f is a function of u and t. So, if you take u double prime, that will give you the partial of f with respect to t plus f times f u, and the following term, the third order term would have many more such combinations, f t t plus 2 f f t u plus f square f e u plus this, and so on and so forth. So, we could keep on writing it all down, and the way we have written down k 1 was simply h of f evaluated at the previous gate, and k 2 we said would be h of f evaluated at t n plus C 2 h and u n plus A 2 1 k 1, right. So, that is the expression for that. So, if I expand this k 2 by h, that is basically a Taylor series expansion of this about t n and u n, and that gets you there. So, basically you have this k 2 by h, and then finally what you need to do is you would be writing this is w 1 k 1 plus w 2 k 2. You have this expression for k 1 and k 2, and then you keep using those informations in terms of u and f, and this is what you get. U n plus 1 should be u n plus w 1 into h f plus w 2 into h, and these are those expressions that we have written it down. The Taylor series expansion of that expanded about at t n would give you this whole set of terms. So, basically talking about a second order method, all you would be interested in writing down the coefficients on either side of order h and order h square. Order h you can very clearly see here the coefficient is would be analytical expression would be 1 itself. Okay. So, that is that h itself the coefficient is 1, and whereas here you are seeing that it should be w 1 plus w 2. So, that is your order h condition. Similarly, order h square would give you, from here you can see this w 2 h into h c 2 f t will be one such term, and then there would be another term coming from here w 2 h into h a 2 1, and that is multiplied by f f u, and if you look at the corresponding analytical expression, this is what we have. So, this is your del u double prime. So, this is basically u double prime here is nothing but this quantity half times f t plus f u. So, what you notice that 51a is a direct equation that you can work with. What about this? This equation somehow depends on your problem. because the problem defines your function f. So, what happens is that for a general methodology you should not be talking about any arbitrary function, but if you do, then what you note that this coefficients of f of t and the coefficient of f f u must also independently match, because that would be the most general way of doing it, and if you do, that would actually yield two conditions. Okay. So, basically you have one condition from order h and two conditions from order h square, that gives you three relations, but you have four unknowns. So, easiest way is to solve it parametrically. You choose any one of them as a parameter, let us say that be C 2, then you can immediately see that from this equations you would get A 2 1 equal to C 2, and W 2 you can work it out from here, and W 1 is 1 minus W 2. So, that will give you this condition. So, basically we have solved it in terms of the parameter C 2. We still have to decide upon how we go about fixing C 2, but I may draw your attention that what we had done, we had taken T n and then we added a fraction of the time step to go to the intermediate stage. Whenever you have explicit dependence on T, you call such systems as non-autonomous, right? They are called the non-autonomous system. In contrast, you can have autonomous system where the T does not appear explicitly. So, you would not have this part. If you do not have that part, that is what we call that as an autonomous system. So, that means we are talking about something like C 2 equal to 0, but then you may say that this looks difficult because C 2 appears in the denominator. It is not that difficult. You can work from the first principle and develop that. We will be actually doing one such example of autonomous system, and we will work out for a higher order system, and then you will know what I am talking about. So, if I now write down everything in terms of C 2, then u n plus 1 would be u n plus this two weighting functions times the increment k 1 and k 2. So, one way of fixing C 2 would be to look at what we have omitted while working out this strategy. That would be the next term that we have omitted, that would be order h cube term, which is nothing but this, okay, which is nothing but this, and since W 2 C 2 is h 2 h, so we can plug it in there, and then we can see that the truncation error term is the leading term, order h cube term, which will work out like this. Okay. So, we have the leading truncation error term written in terms of the right hand side of the equation that we are trying to solve, plus our choice of C 2. Now, there are various ways of looking at it, how to fix C 2. There is something called Lotkin's bound, which tells you that you could work out an estimate for the quantities that you see in your truncation error, that would be del t I del u j. So, this mixed derivative is bounded by this Lotkin's prescription, that will be L I plus j m to the power j minus 1. So, your I and j would of course go from 0, 1, 2, etc., etc. So, if you do that, you can immediately see what you get. Suppose I choose I equal to j equal to 0, then that would give me an estimate for f, right. So, mod f would correspond to I equal to j equal to 0, that if I put that, that would give me this bound, that mod f should be bounded by m. Now, if I look at this partial derivative, so that would imply what? I equal to 0, j equal to 1, and that would be bounded by this quantity L and M. L and M are some finite bounds, okay, finite numbers. So, that we do not have to know in general, but for given specific function we can work out these quantities. So, f of t would be similarly I equal to 1, j equal to 0, and that will give you this, and you could work out similarly the other relations f of t t, which is I equal to 2 and j equal to 0, that would be bounded by L square m, and f t u would correspond to t equal to I equal to 1, j equal to 1, and that would be bounded by L square, and this will be bounded by L square by n. So, if I use this information from this bounds, then you could see that t n plus 1 would be bounded by m L square, and we are looking at the leading term as that, that would be 3/1/6 minus C 2 by 4 and plus 1/3. So, this is one way of looking at the problem. So, what we are saying that this leading truncation error term would be given like this. So, basically in a sense we have substituted these bounds in this last equation 55, that yields this coefficient as 3, and this one gives you 1/3. Okay. So, basically then you can immediately see that this will be minimum if I choose C 2 in such a way that this quantity here is equal to 0, right. So, that is one way of doing it. However, we need not have gone through all this. If you are smart enough, you can immediately reason it out here, that for any arbitrary choice of f, you can see that this we do not have any control, right. So, only thing that you can exercise control in reducing the truncation error would be to put this first set of term equal to 0, and that immediately suggests this coefficient equal to 0. So, without even bothering to work out all this bounds and etcetera, your common sense will immediately tell you that if you put this quantity in the first bracket itself equal to 0, then you are done. So, that is equivalent to choosing C 2 equal to 2/3. Okay. So, this is one way of developing a Runge-Kutta method. So, you choose C 2 equal to 2/3, that will immediately give you A 2 1 equal to 2/3, and you can work out W 1 and W 2 like this. So, this is essentially the step that you would be doing in writing a program, that you could write K 1 and K 2 in terms of this, okay. And eventually W 1 and W 2 will assist you in fixing the solution at the next step. So, that is one way which ensures reduction of error. So, that is the choice. Well, you could also see that here if I would choose C 2 equal to half, then W 1 becomes equal to 0, right. And then what I need to obtain is just simply W 2, and then I can get this solution in terms of K 2 alone, because W 1 equal to 0. So, this is what is called as modified Euler-Cauchy method. So, it is a multi-stage method, no doubt, but again what you would be doing is you would be evaluating K 1, but you do not need to store it. You can instead directly obtain K2 and obtain the solution at the next step in terms of K2 alone. So, this is the way that these methods are worked out. So, if I want to go a little higher, for example, we are looking at a 4th order method. So, that I will call as RK4 method, Runge-Kutta 4-stage method, and let us make our job simpler by considering an autonomous system. Although it may appear to be sort of a big restriction, but you would come across most of the practical problems that you would encounter would be of this class. Okay. So, most of the problems that we come across in computing belongs to autonomous class. So, that giving up the dependence on T is not a very serious one. So, the method that we are going to talk about are going to be quite useful. Okay. So, since we are talking about 4-stage method, we would be evaluating all this 4 increment functions K1, K2, K3 and K4, and you can see the pattern that you do not have dependence on T, but you have dependence on U alone. So, the K2 will be incremented by A21 times K1, K3 will be incremented by A31 K1 plus A32 K2, and K4 would be incremented by this previous 3 increments K1, K2, K3 here itself, and final solution would be the weighting of all these increments. Okay. So, all that needs to be done is essentially the same step that we have worked out just now. We will be working those expressions out for the Taylor series. So, if I look at K2, so define A as equal to K2 by H, then we can expand it, and this is how it is. Notice that K1 itself is H times F. So, you can plug them in, and what you are going to see that K2 will be H times F, and there would be this gives you a H, and there is another H. So, it will have the second term H square A21 F Fu. Okay. The next term would come from here, that will be H cube by factorial 2, and there is a A21 square, and we have F square coming from here, and this FUU remains as it is. And the next term would give you this. By now, you have realized that having chosen the method order of the method, you just need to keep terms up to that order only. Okay. So, that is what we are doing. We are just retaining terms up to H4, because it is a 4-stage method. Okay. So, that is your expansion for K2. Similarly, K3 would work out like this, and you can notice that you have to use all this information on K1 and K2 in K3. It is a little involved, and you get this whole set of terms when you retain terms up to H4 alone. You realize that if I were to be doing this exercise for a non-autonomous system, it would be a lot more tougher, because there would be Ft and F mixed derivatives would come. That is why I tried to keep it controlled, to look at the way these methods are developed for this autonomous system. Non-autonomous system is little more involved. Okay. So, the last thing that you need to do is find out this K4 quantity, K4 by H, that would give you this, and you can notice that what you have here is F41 K1, F42 K2 and F43 K3, which itself is a kind of a series of terms, and if I keep in that series of terms only up to H cube, because there is a H downstairs here, that would make this overall series on the right hand side as H4, and that is what we need to do. So, that is what we do. Do a little bit of algebra, and this is what appears as a intermediate solution for this increment K4. Having obtained these expressions for K1, K2, K3 and K4, you go back and plug it in that expression where we have written down un plus 1 in terms of un and this increments k 1 to k 4, then you would have obtained a series where we have retained terms up to h 4, and then what you do is you compare that series with the Taylor series expansion of u t 1 u t at n plus 1 in this fashion, and go on till h to the power 4. That is your last line of that slide tells you, and equate term by term. Once you start doing that, since you have access to this material, I am just not bothering you with all this derivation on the board. You can convince yourself they are the ones that will appear. So, the lowest order term will tell you that this W 1 to W 4 adds up to 1, and that is what you would expect, because we are talking about weightages. So, all the weights should add up to 1, and that is what you are seeing here. Look at order h square terms, that will give you this. Okay. There is no problem there. However, if you look at order h cube term, you would once again see there would be terms which are coefficients with f u square, and there would be terms which are f square f u terms multiplied to that. So, if we equate the Taylor series with this algorithm and then equate the coefficient of these two sets of terms as we did before, then order h cube will generate two equations. Okay, two equations, and that is what we have written down here. 62 and 63 are those terms corresponding to f u square and h square f u. Same way, you look at order h 4, and there you would have terms which are multipliers of f cube f triple u, f square f u, f u u, f triple u, and f u cube. Okay. So, if we match this three sets of terms, that will give us three more equations. So, what we have now, we have from order h one equation, from order h square one equation, order h cube we have two equations, order h 4 three equations. So, all together we have 7 equations. How many unknowns we have? We have those 4 weightages W 1 to W 4, and then we have A 2 1, A 3 1, A 3 2, and A 4 1, A 4 2, A 4 3. So, there are 10 unknowns. Okay. Now, so that gives you some bit of room to maneuver. What you could do is you could fix any 3 of them according to your convenience, and convenience means you would like to put some of them equal to 0. That would mean lesser number of computation, right. If I set some coefficients equal to 0, that gives me the liberty of not evaluating those sets of terms. So, we look for such opportunities, but if you look at this equation, that should send you a warning bell. It will say, look, be careful, do not try to put A 4 3, A 3 2, A 2 1 equal to 0, then you would be violating the condition, and that would not be there. So, I have written it down that you should really not choose them as equal to 0. What we could instead do, we could pick up, say, let us say the other 3 AIs that equal to 0, because that is what are involved in those increment functions. So, if I trace this 3 to 0, then we can decide to have some kind of an advantage of computing less. And I wanted to bring one fact to your attention, that I have looked at some textbooks, very old ones and good ones, Ralston, and there are some books by Indian authors too. Unfortunately, I could not reconcile to the fact that they talk about 8 equations, and what we are seeing here, that we get 7 equations. So, what happens is, working with 8 equations for 10 unknowns, they give you some kind of a solutions. So, the solutions are, unfortunately the screen got truncated, I do not know what happened today. So, we get this weightages as 1/6, 1/3, 1/3 and 1/6. Okay. And accordingly, some set of conditions are given. So, I asked one of my student, PhD student from maths, to really see what is going on here if we are making some mistake. The good news is we are not making some mistake. Apparently, those books are not reporting something consistent, because as we can see, we cannot have more than 7 equations if I am going up to 4th order. So, we decided to check out their solutions. So, we said okay, we will adopt those weights that they have chosen and then work out for the rest. This is what we get, that 2 of the equations gives A32 either as 1 or 1/2. So, we decided to take 1/2, because you do not want to go in an intermediate step all the way to the terminal point. So, that 1 would be a non admissible solution, right. So, that is what we decided, that we should take A32 as half. If we do that, then we will get A43 as 1, and from 2 sets of equations that we will get A43 equal to 1, and if we take another 2 sets, then we get 2 possibilities, 1 or 1 by root 2, and if I take another 2 equations, then I get A43 equal to 1. So, all this tells you somehow that this 1 by root 2 is odd man here. So, that should not be a valid solution. Instead, if we choose A43 equal to 1, they seem to satisfy 61, 62, 63 and 65, and 64 is already satisfied. So, all it is needed for you to see if that equation 66 is satisfied. Most of the combinations that we get do not satisfy the last equation except this condition, A21 is half, A32 is half and A43. This is a big relief, because what happened is this is exactly the solution reported in those books. I do not know, it is a bit of a mystery at this point, that they have done something inconsistent, they come to some such solutions, and that solution seems to be quite okay. I mean, even if you correct those mistakes, you still get a set of solutions which are the same. Well, this looks somewhat very inelegant. I mean, we have been looking at some kind of a solution which was obtained by someone, we are just checking this. The best thing would be to choose a method where we could minimize the next higher order truncation error term, like what we talked about in RK2 method just now. We looked at the truncation error term, order h cube term, and that we minimized, and that is how we fixed C2. So, we should be able to do similar such exercise. Looks like a bit of a work, and that kind of a possibility always tell you, with all apologies to PhD students, the PhD students have a bit of time to work those details out. So, I have given it to my young friend there to work it out. So, that is the way. So, you basically look at order H5 term and minimize that truncation error term. So, what we are talking about? We are talking about let us say fixing 3 quantities in that exercise as arbitrary, then you have 7 equations, and try to look at the next higher order term in that 3-dimensional space and find out where the minimum is, and that is how you do it. Okay. So, this is all about Runge-Kutta methods, and let me assure you that Runge-Kutta methods are one of the most elegant, physically correct, efficient methods. So, that is why I would not ask you to look for anything beyond Runge-Kutta methods for all your requirements of time advancement for sure, and we will come back to that topic again when we come to discussing PDEs. Now, just for the sake of completeness, I will briefly touch upon multi-step methods you ought to know, because lots of work gets done using multi-step method. So, for example, a generic equation that derives a 3 time level method is written here in this equation 67. So, you have the solution at advanced time level in terms of what you have in the current time level plus what you have stored in the previous time level. So, that is how the 3 time level gets into the picture, and of course, in solving that equation du dt equal to f, you need to evaluate those, and once again we are talking here about autonomous system, because that is what we get. Now, what you can do is you have to fix this coefficients alpha 1, alpha 2, beta 1, beta 2. So, what you do is you write down a Taylor series expansion, right. So, you write un plus 1 in terms of un, and this of course remains as it is. This you also write in terms of un, and we have seen your friend is falling over. So, what you do is you write down the Taylor series of this also that we have seen, okay, and equate term by term, and you get this equation. Alpha 1 becomes 1 minus alpha 2, beta 1 works out like this, and beta 2 works out like this. So, you can once again treat alpha 2 as a free parameter. So, if you choose alpha 2 equal to 1, you immediately see that alpha 1 becomes 0 and beta 2 becomes 0. The method that you get is called a leapfrog method. This is the game little girls play, right? Leapfrog, jump one over the other, one box, skipping one box and go to the next. And tell you what, this is what all the weather prediction people have been doing ever since they started their business. They always use this leapfrog method. I'll come to discussing about this particular method, that after having said that multi-step methods have to be observed, but still it so happens that if you are solving inviscid equation, this method happens to be one of the most accurate method, and that is for some good reason atmospheric science people have been using for decades now. We will talk about it. So, this is one of the methods. You see that 3 level method works out fine, because what happens here, you get 2 modes and both the modes becomes coincident, and that happens to be the physical mode. So, that is the beauty of this method. Unfortunately though, this works only if you are looking at inviscid equation. The moment you add diffusion terms, you would notice that this method will blow up on your face. So, that is a major issue that you would not like to use a priori without knowing pros and cons of the method, and it is a warning to you that appropriate analysis must be performed before adopting a method. This last one I have purposely added. This is done actually advanced by Adams and Bashforth. These are 2, I suppose, scientists in Cambridge in 19th century, and they were solving some problem of surface tension, and they worked it out that they could do it by hand, and they did come out with this method. What it does is it advances the solution in terms of the current solution and this right hand side here. Right hand side evaluated at the current time level and the information obtained at the previous time level. The bad news about this method is it is overly glorified. Lots and lots of people use it. In fact, if you go and use any search engine, you will find that lots and lots of people are claiming that they are doing most accurate calculation using this Adam-Bashforth method, which we will see that it is not really a good thing to adopt. I purposely mentioned that Adams and Bashforth, when they developed, they were using their I would say brain power to work it out by hand. So, they did not do many time steps, and that is why they did not probably realize the pitfall of the method, and which we did about few years ago, and we did report it in a couple of papers. And warned people, but looks like the warning has not registered. People still continue to use. So, this is something. So, having come to a bit of a discussion about ODEs and their solution methods, I try to bring in a little bit of advanced topic, and that is what is called as a stiff differential equation. However, that may not appear to be such a oddity for people coming from chemistry and chemical engineering. Stiff differential equations are those which are, of course, very stiff, resistant. What happens is, if you try to integrate them, you would see that there are components of solutions which vary completely differently. Okay? So, if I talk about a set of equations, so what we have written here is a sort of a vector equation. U prime means u1 prime, u2 prime. I have written it in a columnar fashion, and the right hand sides are functions of time plus, let us say, all those ui's. Okay? And what you have, let us say, you are provided with a solution at the starting gate at t0. Now, what you can do is, this is a set of, let us for the moment talk about a linear system. So, what you are going to see is, this is a set of coupled equation, okay? And you could write u prime equal to some a u, okay? And that a would come from this partial derivatives, what we call as a Jacobian. Okay? So, this is nothing but del f del u1, del f del u2, and so on and so forth. So, you can fill up a matrix, and that matrix will have a m eigenvalues, right. We have an order of the system m. So, we will have m eigenvalues. What happens is, you can work out a ratio which we will call as a stiffness ratio, that is nothing but the quotient of maximum for the real part of lambda I and minimum of the real part. So, that basically tells you that in that system something is going with this kind of rate with time. That is what it means, right, real part of time. So, we have generic solution as e to the power lambda t, right. So, the maximum growth rate would correspond to this part, growth or decay, because we are talking about modulus. So, it could also be a decay rate also. And you have a complementary part which will be just on the other end of the spectrum. If you look at this ratio, if this ratio is too far apart, then you have all kinds of problems. Why? Because your numerical requirement will be tied to these extremes, right. It is almost like a poor man's blanket, you know, you try to cover up this part, that part will be exposed, and vice versa. So, what happens is, you have to be really conscious about it. As I mentioned about this example from chemistry, this could relate to, say, simple chemical equation. So, you have a forward part of the reaction and the reverse reaction, and you know the forward part, of course, goes at a very higher rate compared to the reverse reaction in most of the stable reactions, and that gives rise to a regular problem of stiffness issue, and that is what I thought I will explain to you. There was this equation that we have been looking at recently, relates to stability of physical systems. This was proposed originally by Landau. Some bit of work was done by Stewart, and later Eckhouse contributed to it. Eckhouse's contribution comes through this coupling term. So, suppose let us say we have a 2 degree of freedom system given by A1 and A2, and we are looking at its time rate. Now, what you notice that this part, the first term corresponds to the linear growth rate. Suppose I remove the second and third term on the right hand side, then what I get, dA1 dt is alpha 1 A1. So, I can immediately integrate, and I can see A1 goes as lambda 1 t. Same way A2 goes as lambda 2 t. Now, this term, the second set of term, which was a bit of a mystery, Landau suggested, but never shown the proof, and he did not completely tell us how he got it, but that seem to work out very fine for some systems, and you would be surprised to see that people use it across many disciplines, not only for what he intended in fluid mechanics, but it has been used even in quantum mechanics. Landau-Ginzburg equation people do use, it is a variation of this equation. So, this second term that you are seeing here, this one, this second term here and the third term here, that gives rise to what is called as a nonlinear saturation, because this one, the first term, that we are seeing tells us A1 goes as e to the power alpha 1 t. So, if I plot A1, then from a quiescent condition it will perhaps start growing exponentially. That is what it means if real part of alpha 1 is positive, that is what it does. This second term that we are seeing here, beta 1 1, this that has this tendency to saturate that, and this is very often seen in physical systems. So, that is a basically nonlinear saturation term. Okay. So, that gives you eventually an envelope which goes like this. So, you get a stable system description. In fact, those of you who have seen or attended any course on fluid mechanics, you may have seen that if you keep a bluff body in a flow, you get this vortex shedding which comes out in a nice manner, right. You get alternate, from the alternate side you see that shedding. That is very well captured by this Stewart-Landau equation. However, for some situations, for some parameters, these do not work very well, and that provoked Eckhouse to add this coupling term, which was done by one of our students recently. We did look at it, and what we find that whenever you are looking at it, let us say you have predominantly a single degree of freedom system A1, but somehow another mode also comes into play which you cannot neglect for all time. So, then you need to worry about this third term here and this second term here. However, now what happens, you see A1 may go at a higher rate and A2 contributes very little, but still its presence has to be there. It is exactly like your forward and reverse reaction. You want to talk about the equilibrium, you will have to keep both. So, here is a similar scenario. To maintain the equilibrium, you need to have this cross coupling terms, and what happens is this coupling is rather weak, and the moment this coupling becomes weak, you are looking at a large value of the stiffness ratio. So, what you find that when you are looking at the dynamics of a multimodal systems not dominated by single modes, or if you are looking at higher order differential equations, you would often face stiffness of differential equations, and this is not imaginary, this keeps happening. So, to illustrate it, we have chosen a couple of ODEs, looks little odd in terms of these coefficients, but you solve it out, it looks like this. It is a synthetic problem, so you can see we have purposely concocted this solution to really work out two fundamental modes. One decays with time as e to the power minus 2000 t, the other one is much more gentler in its decay, it is e to the power minus 2 t. So, one is decaying rapidly as compared to the other. So, you might as well say why should we even bother, this is anyway going to disappear in a short time. So, we do not really need to worry about e to the power minus 2000 t, but then life is not always that simple. You will not guess the solution. If you knew, you would not be doing, you would be given handed down a couple of coupled equation, you will have to be solving it, and if you solve it, you would find that the time step requirement that comes out from the numerical instability point of view, which we will talk about later, puts a very restrictive condition on the amount of time increment that you can choose. So, for this equation, depending on this stiffness ratio, now you can see this is about 1000, stiffness ratio is 1000, and the time step is restricted to 0.0014. So, even for such a simple looking linear equations, you would have to spend a lot of effort. You cannot just simply say I will not worry about it. If you say that, you will see to your peril that solution process will break down, you decide to take anything larger than this. This value of delta t essentially tells you that you are capturing this. Without capturing that, you cannot go ahead. Well, mathematically speaking, this is about the coupling of the equation. We have two modes, and when we compute, we also have what we call as the round off error, right. You cannot compute without round off error, and what happens is round off error would always be there, because your set of equations have both the modes. Although this mode by itself does not say its importance, but then when you are trying to obtain a numerical solution, you have to do the same thing that you do analytically also. You cannot just simply get a solution without both the modes being present, right. So, what you need is a what we call as what do we call? We need to keep a solutions where all these modes retain their linear independence, right. If one part of the solution becomes dependent on the other, then you have numerical contamination, the solution breaks down, and that is what this stability limit is telling us, that if I do not take small steps, I would not be able to retain both the modes and I will lose linear independence. So, what happens is the parasitic error, which is given by this riding of the small sources of error like round of error, rides on what seems to be benign and does not affect the solution, but those errors ride on those unmodeled path, and eventually solution blows up. That is what it says. So, classically what used to happen is people used to use a method called trapezoidal method to solve at least this class of problem given here. So, if I talk about the system of two equations here, okay. So, dy 1 dt equal to f 1 and dy 2 dt equal to f 2, then the trapezoidal method would involve evaluating this right hand side as a weightage of the function evaluated at the current time level and the function evaluated at the next time level. So, basically this is how we go about, and if the equations are linear, it works fine, but if there are nonlinearities, we will have to work little harder, and in some cases even for linear equation this does not work out. So, this is what we are going to talk about at tomorrow's class.